Great.
All right, take it away, Eric.
Thank you, Tom, and the other TASI organizers, of course, Ethan, Oliver, Tom, for asking me to lecture here. And I myself was a TASI student. It's a shame I can't be back there in person, of course, needless to say at this point, but I just want to emphasize to you students that it's not lost on me what you're sort of losing out having to do this remotely. And in connection with that, I understand it's week 4, and that is another 30 hours of Zoom that you're staring at this week. And so I hope that after 3 weeks, you're feeling extra inspired by what you've heard. And I've seen several of the lectures myself, and I really enjoyed them. And that's how I felt after my first 3 weeks of TASI. But you're also probably exhausted, and that's okay. And so I'm going to try to take that into account in terms of the way that I organize my lectures. So I think that if I were to just bludgeon you with formalism, that would end up just going in one ear and out the other, or at least there'd be some chance of that if I were in your position. So I think it's always important to stress the big picture of what one is trying to learn. And so we're really going to spend some extra time doing that, especially today, to get you interested and hopefully keep you interested through these 4 lectures. And so, yeah, we're really going to talk about the big picture pretty much for all of today's lecture. And in the next 3 lectures, we'll talk about how you accomplish some of the things that we'll be talking about. And I encourage questions, maybe even more than usual, to keep yourself engaged from falling off down the steep slope of too much Zoom. So anyway, so that's the philosophy behind today and the days after this. I also, thought about giving a set of background reading, but honestly, I just wanted you guys to relax this weekend. So come into these lectures feeling ready to learn and listen. With that said, now that we're starting, I will be putting stuff on the wiki in connection to the lectures. And I think an important aspect of learning a subject is also knowing where to look to find things out. And so I'm going to try to list copious references in connection with what I talk about. And feel free to ask me at some point today, if you have a question where you can find out more about that, or on the Slack channel. Good. So a quick outline of the way the week will go is that today, so first, what does Bootstrap for AdS CFT mean? I'll be telling you how I'm going to interpret that. It means perhaps what you think it means, which is that we're going to talk about the classification of and properties of holographic CFTs, the sort of taxonomy of this space, and what the conformal bootstrap on the CFT side can tell us about gravity, and to some extent what we're learning about holographic CFTs from gravity, and what a lot of the open questions are. And there are a lot of them, even though this subject is very large and pretty old by the standards of our field. So today we'll really just be talking about the big picture of what that all means. Tomorrow, we're going to talk about 4-point functions and some techniques in computing holographic correlators, which are one tool for answering some of these questions, and what those imply about the space of large N CFTs. That'll continue on day 3, where we transition into maybe a more taxonomic approach to the space of holographic CFTs. And then finally, on the 4th day, I thought I'd give extra attention to AdS3 CFT2, where there are some special techniques that one can use, modular invariance, for example, some of which you heard about in Alex's lectures, but I think mostly you didn't really hear about this aspect of it. And so the 4th day will be largely spent focusing on the AdS3 CFT2 case, and then hopefully wrapping things up, summarizing and talking about some open questions. So that's the ambition, and we'll see if it ends up being as organized as that. But good. And of course, the last sort of administrative comment I want to make is if you have serious questions about string theory, you should direct them to Irene and Natalie. And if you have questions about how physics actually works, you should direct them to Dan Sung. Good. So let's get this going here. Let me share my screen. moment. All right. Okay. Okay, so everyone can see this like I can. All right, great. One day it won't be necessary to ask those things, but I still feel the need to ask. Okay. Good. So, well, one more thing before we really talk about this. So this is a photo from TASI 2011, or 2010 rather, when I went, just for fun. So there are several people perhaps you would recognize. Of course, many people here still in the field, many friendships formed, et cetera, et cetera. Bonus points if you can find me. I'm gonna move on now, but you'll be able to find this in the recording. So here's a fun thing for you to do later, and a reason to rewatch the lecture on recording if you need to. Okay. I see Tom still peering at it, so I'm hesitant to move on, but I'm gonna move on. Good, okay. All right, so these lectures will be about a question which can be phrased in various different ways, but really we're trying to understand in a conformal field theoretic point of view the emergence of space-time from large N. And so AdS CFT has been around for a while, and roughly speaking, I think in the beginning the arrow went more this way, while we were learning about strongly coupled CFTs from AdS gravity, and then, and again, this is a bit of a caricature, the arrow started to shift in the sense that techniques on the CFT side were employed to give us insight into AdS gravity. And today will be sort of more about, these lectures really, will be more about this arrow, although, of course, both relate to and inform the Bootstrap. So what are some of the big questions that we're going to try to answer or touch upon? So the first is, well, what is the space of large N CFTs? And slightly more precisely, what are necessary and sufficient conditions for a CFT to have a nice holographic dual? And of course, the question this raises is, what does nice mean? You might mean something like Einstein gravity coupled to low spin matter. That is maybe a prototypical holographic CFT. And so one wants to understand what conditions on the CFT side one must impose and what the minimal such set is for this to follow in the bulk. And a second big question is that gravity, predicts striking features of holographic CFTs. Can we understand them on their own terms in CFT? Understand or derive in CFT. And of course, there are many more questions under these pretty broad umbrellas. So, and again, please interrupt if you have a question. So, CFT local operators, O, furnish irreps of the conformal group, which is SOD comma 2 in their unseen signature. And this contains a maximal compact subgroup of SOD, that's SO2. And so these operators O will come with some set of spins, J, and a conformal weight, delta. If there are global symmetries, then the operators are also characterized by global symmetry charges. And if the theory is superconformal, then operators furnish irreducible representations of the superconformal algebra. And so in particular, if there's a bosonic R symmetry, then the operators have an R charge as well. And so with respect to the local operator sector, well, sorry, one more comment before transitioning to that. These operators, obey and OPE. So if I take the product of two operators O sub I and O sub J, then I can expand this as a linear combination of other operators O sub K or sum over K. And so from the abstract perspective, CFTs are just lists of operator dimensions and OPE coefficients that obey certain consistency conditions. One of them is unitarity, which places lower bounds on the dimensions of operators, but there are others. The list of such consistency conditions is time dependent. We also don't know what the minimal such list is, and we don't have a fully axiomatic formulation of conformal field theory. So that's partly why this is an evolving subject. But from the Bootstrap point of view, what one is trying to do is to constrain these lists by imposing the consistency conditions we know, such as unitarity. Okay. So the conformal bootstrap. Well, first of all, it's quite a big subject, and you've probably figured out that if you wanted to read a bit about it vis-a-vis background material, you would perhaps read David Simmons-Duffin's TASI lectures from a few years ago. Salva-Richkov has some very nice lectures. And so in these lectures, we're going to implement the bootstrap in a narrower context than its most broad incarnation, but there's a lot to say. And so what is the conformal bootstrap? Well, it's really just an effort to constrain, excuse me, to constrain the space of and the properties of CFTs. And that's pretty broad. And indeed, I think when people use the phrase conformal bootstrap, they mean that to different degrees of generality. So the broad sense is to constrain CFTs abstractly by any means necessary, using symmetries and consistency conditions alone. In other words, not just trying to construct all the CFTs you can, but in trying to constrain what they could possibly look like. There is a, say, narrow version of the bootstrap, which is to impose, oops, let's that. To impose unitarity and crossing symmetry on local correlators in vacuum. Now, tomorrow we're going to talk a bit more about what crossing symmetry is and how one imposes that and what this means. So in the sort of narrowest version, one looks at 4-point functions of local operators in vacuum, and the crossing symmetry follows from the associativity of the OPE of the constituent operators. Of course, there are notions of the bootstrap in between these two. For example, you might look at correlators not in vacuum, And of course, you might be interested in features of CFTs that lie even outside this paradigm, namely the space of extended objects or non-local operators, which so far the Bootstrap doesn't have so much to say about, and I won't have anything to say about. Are there any questions so far? Okay. Good. So what are some prototypical Bootstrap questions? Let me just name a few. The one is to bound the first non-vacuum primary operator dimension. Vacuum primary delta. Over and above those implied by unitarity in particular. So let us draw an axis in delta, and the vacuum has dimension 0, where I just remind you that delta is the eigenvalue under dilatations of some local operator or some state, those two being equivalent notions given the state operator correspondence. And so you might ask, what is how heavy, so to speak, is the lightest operator allowed to be? So how large can the gap between the vacuum and some operator O star with dimension delta star be in a consistent unitary CFT? So you're trying to maximize delta star consistent with physics principles. Another prototypical Bootstrap question is to do the same thing in a given OPE of some operator itself. So if this OPE, say, includes vacuum, say if this was some real scalar primary operator, it would include the vacuum, and then some operator O star, and you want to max, and here I'm ordering them by conformal weight, so you don't want to maximize delta star appearing in this O times O OPE. Another question you might ask is,
could I ask?
Yeah, please.
What's the physical intuition of that second type of thing? Why is this something you would want to bound?
Good. So let me give you an answer that's maybe a little holographic. So if you have, say, a large N theory and O is some single trace operator, then the first operator appearing in its OPE with itself might be a bound state. And so you might try to constrain binding energies with this kind of approach. But more generally, just putting away large N for a second, if you have a 4-point function that you're studying, you might want to know, how large can I make the gap in this particular 4-point function? Say if the operator O is some special operator which exists in some universality class of theories. So it's a way to sort of connect the interactions of the theory to the dimensions, right? Because the operator has to appear in this OPE. And given that, you want to ask how heavy can I make it? So there's some interplay between the OPE coefficients and the dimensions in this kind of question. Those are two separate answers, which maybe are helpful. Any other questions? Okay. Good. So you might ask, what are the universal properties of the spectrum of, say, any CFT implied by crossing symmetry? So
it's a naive question. Is it?
Yeah.
Could it be zero? Like my question is, like, is there any, like, does anybody ask, like, what is the minimum gap, like, or can the gap be zero? Maybe it's too naive.
Usually, one starts by one would. At the outset, often one is interested just in CFTs of the discrete spectrum. And then you are sort of, you'd like to impose in your method that there is a non-zero gap. You can't always do that, actually. And so in 2D, like in the modular bootstrap approach, that can be a little tricky to actually implement. But often the physical interest is in theories with the gap, and then so people tend not to ask that question because they don't care to know the answer. But yeah, you could ask, if I have, say, non-compact CFT, which is, say, one with a continuous spectrum, what does this theory allow it to look like? Then you'd have to ask, of course, different questions than this one, because the gap by construction is 0, and then you maybe want to ask, what shape does the spectral density take, or something like that. Okay. For most applications, though, people are interested in CFTs with discrete spectra, because once you have a continuum, then certain familiar notions diverge. So, for example, the density of operators in any finite window is formally infinite. Likewise, for some OPE density, we have some of our operators weighted by OPE coefficients, and so you can divide out by infinities to make formal notions of such theories. But especially in higher dimensions, that's kind of a weird thing to do.
Okay, thanks.
Sure. Any other questions? Okay. Good. So universal properties spectrum implied by crossing. So what do I mean? So for example, if you have a 4-point function, you've probably seen a sort of cartoon for 4-point functions, which is something like this, where if you have 4 external operators, you might expand it in operators in the intermediate channel in what I would call the T channel, which is the two top operators fusing onto another operator, which fuses onto the 2 bottom operators. We'll set this kind of notation up more tomorrow when we talk about 4-point functions. But you might ask a question, if I have some 4-point function where there is some operator O propagating in one channel, then what does this imply about the expansion of the correlator in the other channel? And so you'd want to know, what does the S channel spectrum of exchanges look like given the existence of this operator here in the T channel? This is a little bit of a different question than the other two, because here we're assuming that certain operators exist, and we're asking, given the existence of one operator, what does that tell me about other operators? But of course, they're more or less similar.
So can I ask a question about that?
Yeah.
So is the use of doing that you might be trying to like find the CFT dual of some, like your favorite AdS, and then that some operators have to be there, and you can ask like whether you can get a consistent CFT with the right properties that you're looking for, or what is
that is one way that is one way to use this kind of this kind of thought process. And actually answering this type of question in CFT is a way of reconstructing the CFT operator content in a crossing symmetric sum of exchange Witten diagrams in the bulk, which we will talk a bit more about. And so indeed, you're in your setup, you have, say, some operator dual to some bulk field, and if there's a cubic vertex which would give rise to this exchange, then by answering this kind of question, you're inferring information about other operators in the spectrum. And in that setting, it's actually double trace operators made of the 2 external guys. But even more generally, one version of this is where you have, so in the non-holographic context, if you have some identical operator 4-point function, and in the intermediate channel, you have the identity, you can ask, what does the existence of the identity, which every reasonable field theory has, imply about the spectrum? And so that statement would apply to essentially every theory.
Okay.
And so that very question is the foundation of what's known as the light cone bootstrap. And the answer for, in that case, what these O primes are on the other side, gives a notion of composite operator that applies to any CFT that works at large spin, and sort of set the stage for a notion of a Regge trajectory in CFTs, which was later formalized by some papers by Karen Huo. So to summarize, yes, you can use this type of technique for holographic CFTs, but also even in non-holographic ones, it can be quite powerful. Okay. And finally, you might be interested in asymptotics of spectral or OPE data in general CFTs or in certain universality classes of CFTs. So for example, if you have an operator, say O1, whose dimension is very large, and then you have some other operator O2, whose dimension is fixed, then you might ask, what is the OPE coefficient of, say, 1, 1, 2, or perhaps some other combination involving 1s and 2s? How does this scale with this heavy dimension delta 1? Understanding this in the limit where delta 1 becomes large is what I mean by the asymptotics of the spectral or OPE data. And this question does have a nice telegraphic interpretation, which perhaps we'll talk about. So here I've highlighted 4 kind of questions that you see when you read Bootstrap literature, and which some of the original sort of Bootstrap 2.0 papers from 2008 tried to answer. And so surely you have seen, if you have read any Bootstrap papers, and of course, if not, that's fine. That's what this lecture series is for. Some plots of the kinds of constraints that people studying the conformal Bootstrap get on this CFT data. So this is very much a cartoon, but let us plot some OPE data. By that I mean dimensions and OPE coefficients against each other. So you might see some plot of 2 operator dimensions and some universality class of theory, say some theory with some global symmetry. And there will be some regions which have some shapes. Okay. And in the plot like this, the regions outside these green areas are meant to be rigorously ruled out by imposing some Bootstrap condition, so usually crossing on 4-point functions in combination with unitarity. So a region out here in this red X area is a region of this delta I, delta J space, which is disallowed. And on the other hand, in these green regions, as far as we know, they may be allowed or are allowed, but this type of technique does not rigorously rule in theories, it rules theories out. So you see plots like this, and as the techniques get stronger and stronger, the allowed regions tend to get smaller and smaller. Historically, theories that we know about have sometimes been found to lie at special points on these plots. So in that case, which happens sometimes, theories that we know about, for example, the 3D icing model, may live at a kink or inside a small island in the space of the allowed conformal weights or OPE coefficients. And in this kind of cartoon, there's this region over here, whose bounds I haven't drawn, and often there are infinite or semi-infinite regions of these spaces which are unconstrained. And that reflects in part that it's hard, at least numerically, to access the large delta region of the CFT data. But what should be emphasized in this kind of caricature is that the plots that are generated this way are rigorous. And so the value is really in the regions that are ruled out. And then moreover, in finding features of these plots where known CFTs may or may not live, but depending on your perspective, perhaps you're interested in trying to find new theories we had no idea about, or trying to understand how special the theories we already knew about really are. Okay.
So can I ask something general?
Yeah. Yeah.
So does the Bootstrap ever allow you to make any strong converse statements like these theories are ruled in, like regions where you say these exist?
I would say, strictly speaking, no. And so certain, but I would say that's when I say no, I'm referring to, for example, just the kind of vanilla attempts to solve crossing for some set of correlators. Often this is done numerically, you get these plots. Regions are not ruled in using that technique. But there are certain arguments, analytic arguments about the structure of CFTs, which are just rigorous and true. And so those arguments may not rule in whole theories, but they're telling us definitely true things about CFTs. So there's a kind of duality of the approach. And with some of the techniques you learn things for sure, and with other techniques you get kind of circumstantial evidence for existence of CFTs. But what you're really doing is ruling things out. With that said, there are some more recent advances where people are able to, let's say, draw kind of contour maps in these maybe regions where the parameters of the problem are varied, and they can sort of estimate likelihoods of theories existing by asking how the edges of these regions move as they change the parameters involved. And so that's kind of taking a step closer toward answering that question. In other words, it's giving a kind of statistical answer of whether a theory exists or not, but it's not a binary, right? So
that's very interesting. Thank you. Yeah.
Sure.
I have a question.
Mhm.
Is it possible to have a point with an open neighborhood that's completely empty?
Sorry, so you're imagining a point where there is a theory, and then
Yeah.
an open neighborhood around it where there is not a theory, where theories
Yeah.
are dis. For all we know, yes. Yes, I mean, I think in some, this might be a matter of personal philosophy, but that might even be argued to be the generic situation in certain regions of CFT space, where the average CFT doesn't have any continuously tunable parameters like exactly marginal couplings. And so without supersymmetry, without any other sort of super structure, one might expect that CFTs are dotting the landscape, but they're isolated. Certainly in this sort of more narrow sense of, are there exactly marginal directions or not? I think the sort of folklore is that without supersymmetry, CFTs could not have exactly marginal couplings absent any fine tuning that would keep the dimension of some operators to be exactly equal to D. And so in that sense, yes, CFTs should be isolated. And I think that amounts to answering your question with a yes, but the space of CFTs is rich, and we don't, there are cases of interest where there is supersymmetry and so on. So some cases would be like that, some cases would not, but I might say the generic case would be like that, yes.
Okay, thank you.
Sure. Other questions? Okay, so I want to emphasize that, again, this point that from the Bootstrap perspective, CFTs are lists of this operator data, and we don't get to see what operators are made of. That's not a good question from the Bootstrap point of view. You have some list of dimensions delta, some OP coefficientCijk, and you don't get to ask, what is this operator? What's inside the operator? And so a nice type of example to keep in mind is really thinking about, conformal gauge theories, where the observables are gauge invariant, and so the local operators, which themselves are gauge invariant, carry these quantum numbers. And from that perspective, we don't get to know whether it's, what the constituents are that make this trace inside this trace to make something gauge invariant. And so maybe it's a little differently. Conformal gauge theories, from the Bootstrap perspective, there is no n. So, for example, if you had some SC1 gauge theory that was conformal, you really shouldn't think of there being an n. Instead, you should think of there being some central charge which captures the number of degrees of freedom. So, for example, every local CFT has a stress tensor, and the 2-point function of the stress tensor is equal to a certain structure determined by conformal symmetry, let's say rho sigma, times a constant, which is usually denoted as CT. So CT is a central charge. In even dimensions, this is related to the central charge C appearing in the Weil anomaly, but CT exists in odd dimensions as well. And so you can think of this as a kind of general notion of the amount of stuff in a theory, although you really shouldn't think of it as a degree of freedom, counting degrees of freedom in the sense of the phi theorem. Indeed, CT does not obey a C theorem in greater than 2 dimensions. But instead of thinking of N in a conformal gauge theory, you should really think of CT as telling you, indexing some sequence of theories, say. And a type of example that's especially pertinent for us in this sequence about Bootstrap for AdS CFT is the example of n = 4 super Yang-Mills. Oh, no, that's not good. Sorry, I'm having a little trouble with the shiftiness of the iPad. And here, I mean, d = 4, where this is conformal. Now, you might think, okay, I know about n = 4 super Yang-Mills, and I know it has an AdS 5 times S5 dual, and that's what n = 4 CFTs in 4 dimensions are. But it's not so simple from the point of view of the Bootstrap. So when we say super Yang-Mills, that implies that we're talking about, the Lagrangian gauge theory. And so there is gauge group G. So for much of what I discuss, I'll be imagining that it's SUN. And the central charge of the CFT is bin G over 4. H for SUN, of course, is n squared minus 1 over 4. Now, if someone asks you to construct the Lagrangian of n = 4 CFT in 4 dimensions, then that is unique. There might be some caveat here about possible couplings to some topological sectors, but let's not worry about that. And that has not actually even been shown to be possible as far as I know. But the point is that if you insist on there being a Lagrangian, there's a unique one that has this symmetry. Now, from the Bootstrap point of view, the Lagrangian is a member of the stress tensor multiplet. And of course, every local CFT should have a stress tensor, and the n = 4 supersymmetry tells us that the stress tensor sits in a super multiplet with a bunch of other operators, and that includes the Lagrangian. So let's just list the operator content of the n = 4 stress tensor super multiplet. So we have O2. Now what is O2? This is the superconformal primary. It's a scalar of dimension 2. And it lives in the 20 prime of the SU4 R symmetry, which is the R symmetry implied by the existence of n = 4 superconformal symmetry. So there also in this multiplet are the R currents in the adjoint of SU4. And there's the stress tensor, which is being not the superconformal primary, just like every other operator in here besides O2, which is a descendant of O2. This, of course, is dimension 4 and spin 2. I should write this just for completeness. These have dimension 3 and spin 1. And in addition, there's the Lagrangian, which is a certain super descendant of O2. And there's also the L bar operator, which is obtained by acting with the Q bar supercharges instead of the Qs. And this guy is an exactly marginal scalar. So we learned that any n = 4 superconformal theory in 4 dimensions with a stress tensor must have all of these operators. And that includes this operator L, which is an exactly marginal scalar. And so there is a flat direction. And again, if there's going to be a Lagrangian, then this theory is unique. But I was trying to explain, we don't get to ask to know if there is a Lagrangian from the Bootstrap point of view. So if we ask, is n equals 4 super Yang-Mills the unique n equals 4 SCFT in 4 dimensions? The answer is we don't know. Phrased a little differently, we know that there must exist a stress tensor multiplet, but what else does n equals 4 superconformal theory in 4 dimensions have to have besides this multiplet? The Lagrangian theory has a lot of multiplets which can be enumerated, say at the free fixed point, by writing down traces of the elementary fields in the Lagrangian. Some of those are BPS, some are non-BPS, but besides this multiplet, neither is naively required by the existence of the n equals 4 superconformal symmetry. Not only that, but if we ask, okay, there's an exactly marginal direction, and we know that in the case of the Lagrangian theory, it's the gauge coupling. Well, the gauge coupling is not directly observable. Instead, from the Bootstrap point of view, the dependence of the non-BPS operator data on this exactly marginal coupling is a proxy for measuring where on this manifold of CFTs you are. And so in the general case, you don't get to know the exactly marginal coupling is a gauge coupling. In fact, it might not be if these exotic n equals 4 CFTs exist. It would just be some other operator with an exactly marginal coupling associated to it. And that's where it ends. There's nothing more to say. But we don't know if these theories exist, and that, I should say, is an open question. But we do know some things. So what do we know? And this is where the Bootstrap made a very nice contribution, among other places, of course. So in a paper by Beam, Rastelli, and Van Rees from 2014, I believe, called n equals 4 superconformal Bootstrap, well, they showed various things, some of which we'll touch on throughout the course. They showed that any interacting n equals 4 CFT has central charge C bounded below by 3/4. Now recall, SU2 super Yang-Mills has central charge 3/4, and that's the minimal central charge of any Lagrangian super Yang-Mills theory. But this result here was derived just by studying crossing symmetry of the 4-point function of the superconformal primary and the stress tensor multiplet. That is to say, they assumed the minimal thing needed for this theory to exist, imposed unitarity in n equals 4 superconformal symmetry, and asked what the consequences were. And actually, in that case, analytically derived this lower bound in the central charge, assuming that CFT is interacting. What happened there is really the interacting thing played an important role. They showed that unless C is in this range, then there are certain multiplets which contain higher spin currents. And any CFT containing higher spin currents, which are those with spin greater than 2, is necessarily free. We'll revisit that, I think, momentarily, and also later in the lectures. So this is an analytic result, and you see that it dovetails very nicely with something we knew about the Lagrangian theory, but it derived it in complete generality. So it's an abstract derivation of properties in this explicit Lagrangian n equals 4 theory we know. Maybe this leads you to think that, okay, this is some piece of evidence that the Lagrangian theory is the unique one, period. Maybe not, but this is just a true result, and then one can proceed and see what else one can extract. So that's a taste of the kind of thing that the Bootstrap can do in this even very highly supersymmetric setting, where, I should emphasize it is an open problem to answer this question here in complete generality. Now, many of you are probably wondering, what about AdS 5 times S5? We'll talk about that later. Okay, let me pause here for a moment Are there any questions?
This
Sorry,
is
this is a
also-
very. Oh, go for it.
You can go ahead.
Okay, this is just a very basic question, but can you say again why there is no notion of n for the conformal gauge theories?
Sure. So there is a notion of n for the conformal gauge theories because one has to pick a gauge group which has an n in it. But then, having written down the gauge theory of Lagrangian, you can enumerate the gauge invariant operators, and you can even imagine being powerful enough to track their dimensions across the conformal manifold as you vary this exactly marginal coupling. And this family of CFTs is indexed by n. But from the perspective of the dimensions and OP coefficients of these gauge invariant operators, n doesn't appear as n per se. It appears by way of, say, the central charge or other data in that class. And so that's a sense in which, there's no n. There is a C, and in the gauge theory, C depends on n, and other things depend on n. But if you're just trying to sort of bottom up derive what an n equals 4 SCFT must look like without knowing that it is allowed to be a gauge theory, then instead of using n, you should use C, which is something that can be associated to an operator without, while being agnostic about whether it belongs to a gauge theory.
Okay, thank you.
Sure.
So how do you impose that it's a gauge theory in the Bootstrap?
Yeah, so that's a good question. And so you can, if you want to go outside the realm of local operators, then there can be ways to do this, but I think that's sort of dodging the question because that's not strictly within the realm of the traditional Bootstrap. I'm not so sure what a good answer to that question is. Other people might have answers, but I feel like I don't have a satisfactory answer to that.
Sorry, when these people did this Bootstrap for n equals 4.
Sorry?
Like, so when you mentioned a paper which did it for n equals 4 super young, did they impose it's a gauge theory or no?
No, absolutely
Or
not.
just
So
n
that
equals
was the
4.
key point.
Okay,
Yeah.
I see.
So they
It doesn't
said,
have to be gauge theory. N equals 4 SCFT.
That's right.
But yeah.
Yes, they imposed the existence of the stress tensor multiplet, the fact that the operators organize themselves into representations of the n equals 4 superconformal algebra. They imposed unitarity and crossing symmetry, and that's it.
Okay, thanks. Yeah.
So, you might also say, so the gauge theories realize a discrete set of central charges. Can you have an n equals 4 theory with central charge equal to 3/4 plus pi? If you just believe that the Lagrangian theories are the only ones, then the answer would be no, unless there's a dimension of a gauge group equal to 4 pi that I'm not aware of. But yeah. Any other questions? Okay, so now we're going to transition to large n. And so, good. So Bootstrap for AdCFT, what this really means is trying to bootstrap the space of large n theories and make contact with bulk physics. So what do we mean when we say large n? I want us to define this with a little bit of care. And I know, sorry, I realize in the context of the previous discussion, saying large n is a little bit misleading because I just said there's no n. Nomenclature is such that we often use large n to mean large central charge. And by saying n, we're not committing ourselves to there being a gauge theory or anything else. So I'm sure that during this set of lectures, I'm going to say large n, when really you should just think of that as large C. But I guess I set myself up for that clumsy transition. But okay, so when we say large n or large C, what do we mean? So let's imagine there's a family of theories with increasing central charge. And these theories we'll call T sub I. So we're imagining that we have some sequence of CFTs. Such that there's some limiting theory, or some limit one can take on the sequence where in the limit, the limiting theory exists and has large central charge in the limit. So what does exists mean? Well, this means that the limiting theory obeys CFT axioms or consistency conditions, which axiom in quotes here, and that the observables are finite. For example, the partition function. So of course, C in this theory is getting very large. So when I say finite, what I really mean is something like this. If you ask, what is the number of operators with conformal weight below some finite delta star of order 1, if I integrate the density of states from 0 up to some finite delta, that this should be finite. So in the large C limit, you have some sequence of theories, and the density of states is such that it doesn't diverge below some finite dimension. If you look at densities of states of operators whose dimensions are of order C, well, C is becoming infinite, and so those densities of states are free to sort of diverge in some manner with C, and indeed they do. In 2 dimensions, the Cardy formula has a C in it, but that's just part and parcel with the existence of this large C limit. So this is just slightly more formally what we mean when we talk about a large C CFT as a sequence. Let me imagine taking the sequence such that the central charge becomes larger and larger, and we can eventually perform a perturbative expansion around large C. There may often be other scales in this sequence as well, besides the central charge, and so that will be important. Now, there are challenges for the large C bootstrap, which we'll talk about in a bit more detail in the 3rd lecture. Because as you take a large central charge limit, it can be harder and harder to impose the consistency conditions. And one might get tripped up in trying to distinguish between families which asymptote to large C and theories which are sort of sporadic in the landscape but have very large but finite C. We're not very good at answering that latter question. But even in this sort of safer setting where we have a sequence of theories, there's a lot to do and understand. So now let's recall the AdS CFT dictionary, which Mukund discussed nicely in his lectures. So if we have some bulk field phi I, some elementary fields in AdS, and here I'm going to be somewhat quick. And I'm imagining this bulk field phi I to be light, so it has, say, an order 1 mass, or at least a mass that doesn't scale with Newton's constant. Then we think of this as being dual to a single trace operator, O sub I. We can have composites, say phi I to the n, of the bulk fields, which are bound states in AdS, and those are dual to multi-trace operators, which are, roughly speaking, just composites of the single trace operator on the CFT side, which are themselves conformal primaries. In AdS, you have a mass associated to these fields, and on the CFT side, you have a conformal weight, and the relation between the two is enforced by the equations of motion, which, say, for scalars, is this. And for other fields of spin, it's something else. And finally, in the bulk, we would have cubic vertices, and in the CFT, we have OP coefficients. And the dictionary is such that the OP coefficients are equal to the vertices times some kinematic factor. And the kinematic factor just comes from doing this 3-point Witten integral. The explicit form of the factor is not important at all for what I'm trying to say, because all I'm trying to say is that when we talk about a space of CFTs, well, likewise, there's a space of theories of quantum gravity in AdS, and we can imagine making plots that look just like the ones before, where we say plot some masses or vertices against each other, and there are some regions which may be allowed and regions which may be not allowed. Okay. And so the bootstrap for AdS CFT is trying to understand the map between these spaces. which types of theories on one side look like which types of theories on the other. And in situations where we can meaningfully constrain one side, we can import that to the other and learn something. So, there are a lot of prickly questions in quantum gravity. AdS CFT tells us that at least formally, they can be rephrased in terms of a local conformal field theoretic description, which may be easier to work with or more trustworthy. And so that, I think, is a lot of the power of the Bootstrap in the holographic context. Answering questions about conformal field theories in a totally controlled setting tells us things about quantum gravity in AdS, at least, which are hard to access or even formulate otherwise. Okay. So we can talk a little bit about different types of bulk theories. And so I won't talk too much about this, but I mean, right now, although it'll be at the core of what we talk about sort of throughout the sort of lectures. So if we look at classical theories, AdS, there are different types. Right? So here, this 2D plot of, where n is on one axis and lambda is on the other. Here, I'm imagining we take large n, and we can just ask ourselves what kinds of classical theories of quantum gravity and AdS are there. And so maybe let's draw this a little differently. So I'm going to cap it off just for clarity. So on one end, so we can think of this as interpolating in the coupling, which I'll call lambda for now. Okay. So over here at strong coupling, so lambda is very large. We have theories that look like Einstein gravity or supergravity coupled to matter. Right? So these are, in a sense, the nicest types of bulk theories. There is a derivative expansion and a two-derivative order. It's Einstein gravity suitably dressed. And lambda in the bulk is something like the string length, which is much larger than the Planck length, but much smaller than the AdS radius. Okay. So let's, I guess in the D3 setting, it's this. So let's just keep this in mind as a kind of mnemonic. On the other hand, you can have theories which are much sort of uglier, more complicated than Einstein gravity or supergravity. And these would be theories that are like some sort of higher spin gravity. Or Vasiliev type theory. Now, when lambda is small or order 1, actually this relation does not literally hold. So when you think about the D3 example as trying to orient you, you should think of lambda going to 0 as corresponding to LADS approaching the string length. So the AdS and string scales are comparable, and there's no separation of scales there. Okay. So often when we talk about holography in controlled settings, we're talking about what goes on over here. Okay. And over here, well, string theory is still classical, but alpha prime is very much finite. And we have much less control. And these Vasiliev theories are certain theories of higher spin gravity, which means they have higher spin gauge fields in the bulk, which are not known to be subsectors of string theory, but are believed to capture some part of the ON models on the boundary in the holographic dual sense. I won't say much more about this, although I'm happy to answer questions and I've worked on it myself. But part of what we want to understand is what lambda really means from the abstract CFT point of view. After all, we're not really allowed, or we really shouldn't assume that there is string theory in the bulk. If we're trying to understand the space of theories of AdS quantum gravity, then we don't want to input that the bulk theory is a string theory. And so if lambda was supposed to be some power of the ratio of the AdS radius to the string scale, but there's no string scale, well, then what is lambda? What is the abstract proxy for strong coupling? So what is strong coupling abstractly. And so the way I drew this, and of course I said nothing about what happens in the middle because it's exceedingly complicated. There you have when lambda is order 1, the theory is sufficiently stringy that you have to deal with that, but there's not some emergent higher spin symmetry. So it's really just best to think about the 2 endpoints. We will see that strong coupling is, as suggested by this diagram, equivalent to having a large higher spin gap. So what does this mean? That the dimension, delta gap, where this is defined as dimension of the lightest single trace operator of spin greater than 2 is much greater than 1. Now in string theory context, say n equals 4, lambda, the ratio of the AdS scale to the string scale, sort of controls everything as lambda gets large. Things like the Konishi, which is a scalar, acquire anomalous dimensions that go like lambda to the 1/4. But it also controls the dimensions of higher spin single trace operators, which grow with lambda likewise. And so one of the key things that has been sort of affirmed time and time again over the last several years, starting with a paper by Heemskerk, Penedonis, Polchinski, and Sully, which will be the centerpiece of our 3rd lecture, is that having a large gap in the single trace higher spin spectrum is the abstract version of what it means to have a strongly coupled theory. And so this gets us at least a large part of the way toward addressing what necessary and sufficient conditions are for a CFT to have a nice holographic dual. If by nice you mean Einstein-like coupled to matter of low spin. So here I'm previewing a bit what that punchline is by sort of zooming out on the space of theories.
I have a question.
Please.
So if I just talk in terms of the Hamiltonian, if I diagonalize the Hamiltonian corresponding to this theory, that's like saying that there's a big gap between the ground state and the first excited state.
So if you look at so it's a little more subtle than that, because you need to just be talking about the higher spin states, first of all. And second of all, you need to be talking about the single trace higher spin states. So in other words, elementary fields, as it were, in the bulk. If you have a scalar field, which is light, that's okay, right? That doesn't spoil this condition. And moreover, composites of the scalar field will have spin. So if you have 2 blobs in AdS, they will mutually orbit around the center of AdS and the Hobson angular momentum, and that will be a conformal primary in the dual CFT. So when we formulate this condition, we're talking about the single trace higher spin spectrum. And if this leaves you wondering, well, where does that come from? Well, one of the features of string theory is that strings come with infinite towers of higher spin excitations. And so sort of abstracting from the pictures that we know and love involving D-branes, the piece that seems to be relevant for understanding at an abstract level what acts as the coupling is the gap to this type of operator, which comes for free in string theory, but more generally, defies some other characterization in the Bootstrap philosophy that I've been trying to explain. Does that help?
Yeah, thank you.
Sure. We really will talk quite a bit more about this, especially on day 3. So, good.
Could I ask?
Yeah.
How are you characterizing abstractly what you mean by single trace operator versus multi-trace operator?
So here I'm imagining we have a sequence of CFTs that goes out to large C. And I am, so let's see, what's the sharpest way to say this? You're asking just from the CFT side, it sounds like. You don't want me to use both notions when I answer that, do you? Is that right?
Sorry, my internet connection is a little bit bad.
Sorry, I'm asking. You're asking me to answer that just from the CFT side. Is that right?
Yeah, exactly. If your theory has a description as a gauge theory, then you know what single trace, multi-trace
Yes.
means. But otherwise,
Yes.
I'm not.
Mhm.
Yeah, I've been
So
confused about this point.
Yeah. I mean, I would say it relies on notions of large C factorization in correlators, but you could imagine starting from the ground state, moving up in the spectrum until you hit the next state. Say it's some scalar with some dimension, and looking at some 4-point function of that operator and asking what runs in the intermediate channel, and at infinite C, the decomposition of that 4-point function will look like it'll be that of generalized free fields, where the spectrum is comprised of that operator and all its double trace composites. And so knowing those, knowing the operator dimension, you can sort of delete those higher guys from the spectrum and then ask, okay, what is the next operator in the spectrum? And then sort of do the same thing. So once you identify iteratively from the vacuum some set of operators, then you can just construct the engineering dimensions of their composites and look for them in the spectrum and delete them. That's a kind of algorithmic way you can imagine doing this, but the shorter answer is just that when we assume a large N or large C factorization of our correlation functions, then that makes this distinction sort of easier to ferret out when you decompose correlators. But it essentially amounts to what I said.
Great, that makes sense. Thanks.
Sure. Okay, I have about 6 minutes, so let me return to this. Can you talk a little bit about scales? Now, having introduced this notion of the higher spin gap, what kinds of operators do nice holographic theories have? So I imagine I'll want to sort of return to this plot in the next lecture in view of time, but let me just sort of put it up here. So if we have some scale delta gap, which I remind you is the gap to the first higher spin single trace operator, and we're going to have a central charge in the theory, which is also becoming large, then the operators can be organized according to scale. Right? In terms of the length scales of the theory, we have LADS, L Planck, and something like L string, perhaps, not necessarily, but perhaps. And so if we take dimensionless ratios, then this gives us, well, let me just not call this N, let me call this C. I did it again, C, which is some power of LADS over L Planck. And then something like lambda, which really we know we should call delta gap in the abstract sense. And so we have these two scales. We have a large C theory where delta gap is some other scale in the problem, which is much less than C. And so we have operators that fall somewhere on this scale. So in this range, where operators have dimensions which are order 1, or at least say parametrically less than delta gap, we have light operators. So these sort of form an effective field theory in AdS, where we have some light fields coupled to gravity. So this light sector, of course, includes the graviton. Up here, where operator dimensions are order C, let's call this the second one. These are usually known as heavy operators, where dimensions are order C or greater. And you also have this region here, where operator dimensions are of order the gap. And this is sort of 1A. Let's call this the stringy or higher spin region of the spectrum. Okay. So in the light part of the spectrum, that's what is relevant when one is computing, say, correlators of local operators with order 1 dimensions. Okay, so when you see people computing Witten diagrams involving propagators and so on, as we will, these fields on these legs typically are light fields in the EFT and AdS. And so this can include, includes the graviton, it can include KK modes, etc. up here in the heavy region, well, these operators have dimensions of order C. And so say placing a particle in AdS and turning its mass all the way up to be of order the inverse Newton's constant, then there's going to be back reaction, and you have things like black holes or perhaps conical defects, say in AdS3. And there is another range in here where you can have operators whose dimensions are, say, of order root C, some power of C less than 1. These are like very heavy, sometimes called hefty. These correspond to, say, D-brane type states or determinants. The Bootstrap actually hasn't said much about that, and I won't say much about that, but just for completeness, that's a kind of separate category of states here. So they don't quite back react, but they follow geodesics. Their wave functions are sharply localized. And then you have this sort of stringy region where you would have states like short strings in AdS, where the dimension in a string theory would be some positive power of delta gap. A lot of what we do in large N Bootstrap comes down to understanding what this light EFT region is allowed to look like and how it sort of plays with these other regions and how consistency conditions relate them. So there are many ways in which that's true, and we'll talk about some of them. And to conclude on a note that's related to what we said earlier, but I will definitely pick this up to start the next lecture. In this range over here is where you have KK modes whose dimensions are much greater than 1, but say much less than delta gap. And so this region actually is very interesting in terms of the space of large C CFTs because it contains information about the geometry and the number of dimensions. So recall the n=4 discussion from earlier. We were asking whether n=4 super Yang-Mills was the unique n=4 superconformal field theory. And well, as you know, this theory is dual to AdS5 times S5, in particular type 2B string theory on that background. So if there's some other exotic n=4 theory out there, the bulk dual would be different. And the S5, well, you might say, well, that has to be there because this geometrizes the R symmetry. There's an SU4R symmetry, and that's the isometry group of S5. And we're taught that in AdS CFT, the gauge symmetries of the bulk are the global symmetries of the boundary. And the boundary has this global SU4R symmetry. And that's why there must be these non-abelian graviphotons on the S5. But the S5 comes with a lot more than just that. It comes with an infinite tower of light KK modes because the radius of the S5 is of order the radius of the AdS5. So actually, it's quite a bit overkill if all you're trying to do is geometrize the R symmetry. Or rather, it's quite a bit of overkill if all you're trying to do is realize the R symmetry in the bulk. You could have imagined that there was just a bulk gauge field for the SU4 symmetry, and that's it. But instead, this theory comes with a ton of other stuff, all these light KK modes, which lie in this light EFT region I talked about up here. And so the question of uniqueness of n=4 super Yang-Mills is just one example under a larger umbrella of the question, is R symmetry always geometrized at the AdS scale? By which I mean, are there always large, that is AdS-sized extra dimensions, which contain the currents of the R symmetry on the boundary? And so I think it's a fascinating open question. I've tried to think about it a bit myself, but I'll go into a little more detail about this particular question to begin the next lecture. For now, in view of the negative minutes I have, let me just say that, well, AdS3 CFT2 is special, so we're going to talk about it a little bit separately in the fourth lecture. But just to give an outline, well, a little silly to give an outline of what we already did. Let's say we talked about the big picture. In the next lecture, we're going to talk about correlators and 4-point functions, and a bit about the space of large N CFTs and what these correlators tell us. So we'll compute some Witten diagrams and ask about what aspects of that can be derived from the CFT alone. And that will help us transition into talking about the space or taxonomy of large C holographic CFTs. This is where we'll talk about this Heemskerk et al. Paper, which sort of started the modern version of the subject. And we'll talk about some other Bootstrap type constraints that are used in the holographic setting. And then the last lecture, we'll talk about AdS3, CFT2, plus open questions that hopefully tie everything together. So let me conclude for today.
Thanks, Eric.
I should also say, sorry, I can stay for a while if there are questions, but I haven't been to Gather yet, but is that still happening at 9:30 or
Sorry.
30?
9, yeah, whatever 30. So what we're doing now is just, we'll take a few quick questions that will be recorded, and then typically there are more questions if you have time to hang out, and we'll just hang out in Zoom. We won't go to Gather.
Okay.
There is a Gather meeting at for lunch at 1:30 local time. But yeah.
Got it.
Yeah. So are there any quick questions for Eric?
I have one. So the diagram that you drew, like for the delta, this is only for primary operators, right?
Well, I'm at this level, I didn't need to make the distinction, but maybe you can tell me what you're trying to get at.
Well, what I'm saying is that if you have a light scalar, you can take like 100th derivative of that, and then that would fall like between delta gap and C. But why would I call that operator stringy? Like that's just a light scalar.
Yeah, no, that's true. In that sense, you would not. But it is. But on the other hand, if you add enough momentum, you will form a black hole. But that's kind of not all black holes are primaries. So basically, I agree with you. But you do have to be a little careful about what the bulk dual is in that situation. Yeah, I really do have in mind, indeed, just it's clearest if you think about them as being primaries. Yes. I guess you
One
froze.
question?
It looked like, yeah, sorry.
Oh, did that was
Thinking deeply. I didn't say anything so deep, so I imagine not.
Hey, Himanshu, are you happy with the answer? Maybe you can
Very
put it in the
unhappy,
chat
yeah.
if you're unhappy. Okay, let's move on. Are there other quick questions?
I had one. So do you have some simple intuition for these abstract reformulation of the statement strong coupling? Like why this gap in higher spin states?
Yeah. So I think there are a few ways to answer that, and we'll definitely talk more about that. So in various settings, you can show that if you have say a light higher spin field, say some field of spin 4 or something interacting with gravity and with other particles, then it introduces causality violations or other problems such that it can only be fixed by adding an infinite tower of higher spins that altogether conspire to fix the problem and render the theory causal again. But then if you have an infinite tower of light higher spin fields, whose dimensions are, they're not all, I mean, the unitarity bound scales with spin, so they won't all be light in the delta sense, but they'll have low twist, which is defined as delta minus J. Then your theory starts to look very much not like Einstein plus some small perturbation. So that is what I just said is a kind of abstract version of what you see in string theory, where all the higher spin operators come packaged together as vibration nodes of a single underlying string. But that abstract statement has been shown in various settings without relying on string theory. So that's one statement. If you have one, then you need them all, and then the theory looks sort of violently different from low energy gravity coupled to matter. And another statement along those lines is that if you have often, if you try to construct, imagine that you have higher spin currents. So if you have a higher spin operator which actually saturates the unitarity bound, so it's exactly conserved and it's a current, then at least in CFT dimensions greater than 2, in that situation, you also need an infinite tower of higher spin currents. So that's yet another setting where you see this whole set having to come together. More generally, just forgetting about these types of arguments that seem to abstract away from what happens in string theory, we know that we can couple gravity to, say, scalar fields, or operators with spin 2 or less, by way of just constructing consistent classical gravity theories that have that operator content. And scalars don't do anything bad there, and they also don't contribute strongly in various regimes to 4-point functions where higher spin operators do contribute strongly. Here I have in mind like the Regge regime, although if you're not familiar, then that's okay. So even just by looking at examples, you see that, okay, this is a pattern. It's always the derivative expansion seems to be controlled by the scale of new physics, which is associated with higher spin particles. I hope that helps, but we'll talk more about that.
All right, let's thank Eric, and yeah, so in the recording.